Okay. Hi, everyone. Thank you so much for being here. Today, I'll be talking about, for the first time publicly, about something that we've been researching and developing at Brian in the last few months. And a small gist about me, I'm Paolo, also known as Orbulo. I'm the CTO and co-founder of Brian, and I'm also one of the founders of the Orbulo.eth community and the Ethereum hackathon, and I'm as well a sleep-deprived serial hacker, as I like to define myself. So today, what we are going to talk about is the fact that deep learning models, such as LLMs or diffusion models, are becoming more and more prohibitive for individuals and startups because they are requiring every day a lot of resources in terms of GPU and RAM and not only. And so we can say that neural networks are basically growing in complexity. And when complexity grows, as I just mentioned, so does the computational requirements and memory footprint of the model. Why? Because, of course, more complex models have more layers, more neurons, bigger architectures, and all of this contributes to a huge amount of operations that need to be computed inside the model itself. So for the ones in the audience that do not know how neural network works and stuff like that, I'll be kind of describing them really fast so that you can get the point of both what we are doing and why we are doing it. So neural networks, as the name says, are basically networks of neurons that are organized in layers. Each layer, each neuron inside a layer performs the same operation, and they are called operators. And layers inside the neural network are connected by weighted edges. Adjusting the weights of these edges is what makes a neural network learn. And the weights are often referred to as parameters. So a neural network can be considered large when it has one or more of the following. So when it has a lot of operators, so it requires more computation, or it has a lot of weights, so it requires more memory to store the model itself. We are ignoring right now the training case, and we are going to stick with the inference because this talk is about the inference. Otherwise, we would take also into consideration the training data sites, the training sample data sites as well. So the question that we asked us was, how can we perform inference on a large model on a device that is limited by hardware? Or in other words, how can we use a large model on a device that is not capable of handling the model operators, the parameters, or both at the same time? So we basically started thinking about transforming the more abstract concept of neural network to the more day-by-day, hopefully, concept of graph, where basically data is represented by tensors and computation by operators. A tensor is nothing less than the n-dimensional vector of data that flows through the graph of the neural network. And there are two types of tensors. There are the input tensors and the output tensors. An example of input tensor are the so-called parameter tensors. They are the ones that are used as static input for the operators that we saw before. And when a tensor is the result of the output of an operator, it's called an activation tensor. So performing inference on a model means computing all the activations of all the operators using an input tensor, which in the case of LLMs, it's a textual prompt, and obtaining the output tensor, which is the result, which in the case of an LLM, it's a text, or if you have a diffusion model, you will have an image, and so on and so forth. So the approach that we followed at Brian is to basically, we decided to, okay, let's see what happens if we divide the neural network graph into subgraphs and basically start assigning each subgraph to a particular device. So basically, the idea was to execute inference on these subgraphs by drastically reducing the computational requirements on each single device. The process of dividing a neural network graph into subgraphs is called layer sharding. Of course, when implementing layer sharding inside neural networks, and in a network of devices with different computational powers, that is something that I will be talking soon, there are two main challenges that we need to address. The first challenge is the layer assignment challenge. What does that mean? That we need to find the best way to assign one or more layers to each device. Why is that the case? Because if we divide the graph into layers and we assign layers that require more computational power to devices that do not have that kind of computational power, of course this would cause a problem. The second one, which is not really AI related, but it's more network related, is the challenge of the effective communication. And it's basically the devices of the network where these subgraphs are basically, where the inference is computed on these subgraphs need to communicate in an efficiently and fast way. And also, which is something obvious, messages must not be lost during communication, because otherwise the process of inference would collapse. So before seeing how we want to tackle these challenges inside the network, I wanted to add this little disclaimer here, where basically our ultimate goal with the DCI network is to basically combine the power of crypto incentives with the current state-of-the-art distributed inference techniques. What I'll be showing you comes from the study of different projects, papers, protocol from amazing AI and Web3 developers from whom we took a lot of inspiration to do this. So let's start it. So what is a DCI network? A DCI network is a decentralized collaborative intelligence network, which is a pretty long name, and is a network of nodes that share computational power to execute inference on open source models. What does that mean? That anyone with their own devices, MacBooks, laptops, mobile phones, whatever you can imagine, can join the DCI network and participate with their computational power to the inference of such models. And then at the end, consumers can call the inference on a model that is available on the network, and this model will rely on the shared power of the network in order to execute inference. Then there's also the concept of collaborative intelligence that we introduced inside the name of the network. And by collaborative intelligence, we mean a distributed system where multiple actors are contributing to solving a particular problem by autonomously computing a part of the solution of such problem. In the DCI network context, the actors are the network nodes. The problem is, of course, the inference of the model, and the solution is the result of the inference. So let's start talking about a little bit how this DCI network works and its architecture. So as you could have imagined, the DCI network is a peer-to-peer network, and its topology is constructed via a graph, because we love graphs. And peer discovery, of course, happens to this graph topology. As already mentioned before, any device will be able to participate in this network, and we'll see how, regardless of its computational power. And of course, as any Web3 fashion way, to be a node of this network, you need to stake a fixed amount of tokens, and you will get rewarded with some tokens for contributing to the inference. So we discussed before on how creating subgraphs of a given model allows us to and distribute these subgraphs to multiple devices, allows us to basically reduce or even solve the hardware problems related to executing inference. So now our goal is to find the best partitioning strategy in order to find the best way to assign each layer to each device. A partitioning strategy is nothing more than an algorithm that optimally splits up the layers of a model and assigns them to a node of the network to be computed, basically. So how many of you are familiar with EXO, or have seen some videos about EXO Labs, the EXO project? Okay, not so many. So basically, EXO are doing something similar, but it's more on basically closed environments. So basically you could run really big models on 3 or 4 of your laptops, but it's mainly meant for, as I said, closed environments, maybe your house, your office, and so on. And what is really cool about EXO is they propose this ring memory weighted partitioning strategy, where, as you can see, it's the structure of the network, and the inference follows this ring, basically. And we'll briefly talk about their implementation before the more advanced that I'm going to show you today. So in EXO strategy, in the ring memory weighted partitioning strategy, the network works by splitting the workflow of the inference using weighted partitioning among all the nodes that participate in the network. In simpler words, this means that each device inside the network contributes to the inference using this simple formula, which is basically n equal device memory over the total memory of the network, where n is the number of model partitions that will be assigned to that given device. The device memory is, as the name says, the device available memory for inference, and the total memory is just the total memory of the network. In the context of EXO, the total memory is basically calculated by all the nodes broadcasting basically all their computational power to the others. So in other words, in their strategy, each device contributes proportionally to how many resources it's sharing with the network in relation to how big the network is. And while this strategy works, is really fast and does not include any significant overhead, of course it has some problems, especially if you start attaching crypto incentives to it. As already mentioned, this strategy mainly only works in closed environments, because if you start thinking of just considering the total memory of the network and the memory of the device and so on, you start attaching economic incentives to it, and also opening this network to the public, because EXO networks are not open to the public, but as I said, are closed. This will create a lot of problems, mainly in how we can effectively share the rewards, how can we make sure that nobody is faking the amount of memory that they have, and so on and so forth. So we research, and we are actively still researching, multiple strategies that we could implement inside the DCI network. And I would like to talk about the one that I personally find most interesting and at the same time the most challenging, because of course it requires a lot of work and a lot of research. And conceptually, it's an evolution of the strategy that we just saw. And but instead of being static, where static means that the partitioning changes only when a network joins or leaves the network, because the total amount of memory basically changes. This kind of strategy, we define it as dynamic. And it's, the name is even longer than the Decentralized Collaborative Intelligence Network, and it's called Layer-Aware Ring Memory Weighted Partitioning Strategy. And we just call it Layer-Aware RMW, because it's shorter, I guess. And so this partitioning strategy also takes into consideration the computational needs of each model layer and optimally assigns the most computational intensive layers to the best performing devices in the network. With using this strategy, we can distribute the rewards inside the network in a better way and in a more optimal way. And so we can reward the nodes better, basically. But in order to such strategy, which is way more complex than the first one, we need to perform two types of profiling. The first type of profiling is, of course, the device profiling. That happens when a device joins the network, of course. It retrieves CPU and GPU capabilities and memory capacity and so on, and shares it with the other nodes. And then its capabilities gets tested periodically by the other nodes by sending, for example, probe inferences and so on and so forth to check that effectively the resources that they have declared to have are the ones that they actually have. The second type of profiling, of course, is the one related to the layers of the network, and it's called model profiling. And since all the models usable in the DCI network are open source models, this allows us and other developers that would want to extend the network or extend the amount of models that can be supported by the network, they can profile them and to understand the computational needs in order to match the partitioning strategy that we proposed. The first models that will be supported by the DCI network are the Brian models, and this is because at Brian we will be releasing 4 open source models in the near future, starting with a generic Web3 domain-specific model, and then we will release a question and answering model, a code generation for Solidity model, and at last a natural language to JSON model that is going to be used for Web3 intent extraction. So we will start with these models that will be developed by us, and as I said, will be open source, and we will do some benchmarking and some profiling on the layers of the model in order to see if it actually matches the partitioning strategy that we will decide in the end. So coming back to the strategy. Basically, to sum it up, given a set of layers, that's how basically the strategy works, given a set of layers with their associated computational requirements and memory requirements and so on, a set of devices, and a set of devices, in this case, the network, with their processing powers, at the end of the day, this partitioning strategy means, implementing this partitioning strategy means solving an optimization problem, where the goal basically is to balance the computational load and memory usage across all the devices of the network, or just the devices that have been chosen. So solving this problem means minimizing the computational imbalance between the devices that have been chosen, ensuring that any memory constraints are not violated, and at last, of course, optimizing for minimal inter-device communication. So one of the solutions could be, for example, like solving this kind of problem seems like solving a greedy bin packing with resources constraints problem. For who doesn't know what a bin packing problem is basically an optimization problem where items of different sizes must be packed into a finite number of bins or containers, each of a fixed capacity, in a way that we are going to minimize the numbers of bins used, basically. So imagine you have a lot of bins and you need to fit the items inside of it. The goal would be to basically fit them while minimizing the number of bins. In reality, in our case, we do not really want to minimize the number of bins, because that would be just executing inference on the first device that has the amount of computational power to do so. And so this is why it's not a simple bin packing problem, but it's called greedy, because we do not want to minimize the number of bins. So in the context of the DCI network, as you may have imagined, the items are the model layers, and the bins are the nodes of the network. So implementing this algorithm results in a faster solution, and this is really important for us because we need to also optimize for minimal inter-device communication, but it must be said that at the same time that it's not the optimal one. The last concept that I would like to tell you about is the concept of selective participation that will be present inside of the DCI network, where basically nodes will participate in the inference of model based on the device that they are running on. And this selective participation will be done by dividing the devices in tiers based on the teraflops or T-flops, basically. A teraflops basically refers to a processor's capability to calculate 1 trillion floating point operations per second. So this means that when you hear that a device has 8 T-flops, for example, it means that its processor can actually handle 8 trillion floating operations per second on average, of course. The main difference between T-flops and the other measurement that you have may heard of more, which is gigahertz, that instead measure the processor's clock speed. A T-flop is a direct mathematical measurement of a computer's performance. So that's why we want to take T-flops into consideration. So the goal of selective participation inside of such network is to basically create an opportunity for people participating in this network with maybe old devices or even mobile devices like smartphones to participate in the inference of the network of maybe smaller models and at the same time still earn their reward because they share their computational power with the others. So a little recap with all that I've said from the basically starting definition of what a DCI network is. So the DCI network is a network of nodes that share computational power to perform inference on open source models based on their capabilities and get rewarded optimally based on how much they actively contributed to such inference. This is the last slide, which is more about the dream of what we're trying to do at Brian, and the ultimate goal of the DCI network when it will be released is basically to democratize the access to LLMs by reducing inference costs for users and rewarding node operators for sharing their computational power And what I would like to stress a lot is the fact that the DCI network, for how it works and how we are trying to design it, we are trying to do everything to not force people to rent and purchase expensive GPUs to be part of this network. So our ultimate goal will be to everyone with their laptops to basically participate in the network and get rewarded. So let's bring AI and Web3 closer, one node at a time. That's a little slogan that I wrote this morning. And thank you so much for listening.